So Jazzy, what I'm going to give you here is just a crash course in trigonometry. You will obviously do this later in methods in more in depth, but I'm just going to give you the bare essentials for what you need so that you understand what we're doing in the complex number stuff. So you may have heard that trigonometric functions being referred to as circular functions, and this is because there is a special relationship between trigonometry and circles, and specifically the unit circle. So from last year, you should remember that the unit circle is a circle of radius 1. So that's just radius 1. And we can take a point P that lies on the unit circle, and it's on the Cartesian plane, so we can give it coordinates x and y. And we just call this, this angle theta that this line between the origin and the point P makes with the x-axis, and particularly with the positive direction of the x-axis, we call that angle theta. And we measure it in an anti-clockwise direction, so from the positive direction of the x-axis to this line. So you'll notice then that x and y, if they're the coordinates of P, and that our unit circle has radius 1, then the maximum values, depending on where P is, so if P was right up here, then we'd have a y value of 1 and an x value of 0. If P was over here, we'd have an x value of 1 and a y value of 0. So we see that those Cartesian coordinates, they're restricted in their domain, so they can only be as small as 0 and as big as 1. And that's because of the radius of the unit circle being 1. So from previous, oops, missing a part of a t there. So from previous studies of trigonometry, you know the ratios for sine, cos, and tan, SOHCAHTOA. I'm not going to go through them, I'm assuming that you know them pretty well. So we can apply these to the triangle that we've formed within the unit circle here. So if we have a look at, oops, sorry about that. If we have a look at sine is the opposite over the hypotenuse, so the opposite is y, and the hypotenuse, conveniently, length 1. So y divided by 1 is just y. So that's where we get this relationship that we say that sine of theta is equal to the y value in the unit circle. Similarly, cosine of theta is equal to the x coordinate of the unit circle. And we come to a really important identity here that you should memorize. And that's that if we find the tan of theta, so we find the opposite over the adjacent, y and x, we've just defined y as being sine of theta, and we've just defined x as being cos of theta. So what we end up with is that tan of theta, sorry, is actually equal to sine of theta divided by cos of theta. And that's one to put under your cap because you will use it to death next year, or even towards the end of this year, I think. So, so we measure the angle theta in either degrees or radian. Now, I think you may have seen those before. So to convert from degrees to radian, we multiply by pi on 180. So in one revolution of the unit circle, you know there are 360 degrees, or we say that there are 2 pi radian. You can read about that more if you want to in your textbook, but just keep in mind there are 2 pi radian the whole way around the unit circle, which means in half a unit circle there are pi, in a quarter of a unit circle there are half pi, and in 3/4 of the unit circle there are 3/2 of pi. So I did this weird thing when I was in year 12. I remember saying that that 1 pi is actually equal to a pasty, because if you think a pasty is actually a semicircle in shape, whereas a pi is round. So I was kind of annoyed. Don't know why, but anyway, so a pi is a pasty in my language, but if you sort of think about that in terms of a pi is actually half of the unit circle. So we do, oops, sorry, I'll leave that there. We divide the unit circle into 4 quadrants, and we start with the positive quadrant here being quadrant 1, and we move in an anti-clockwise direction, quadrant 2, quadrant 3, quadrant 4. So if we measure theta, we can also measure theta in a negative direction, and then we call that negative theta. So negative angles go this way, positive angles go this way. So let's just consider a few angles here and work out where they lie within the unit circle. So if we're going to consider the angle 3 pi on 4, so 3/4 of pi, or 3/4 of a pasty in my weird language. Whoops. So 3/4 of pi, 1/4, 2/4, 3/4, it's going to be over there. So we see that 3/4 of pi is in quadrant 2. If we try now minus 5 pi on 6, so of course we have to move in the clockwise direction, so minus 5 pi on 6, so we've got 5/5 of a pasty moving in this direction, so that would be 1/5, 2/5, 3/5, oops, 3/5, what? Fifths, why am I going in fifths? I'm meant to be in 6, 5/6 is what we're looking for, sorry. 1/6, 2/6, 3/6, 4/6, 5/6, so we're somewhere over here this time. So we're neatly in quadrant 3. Ah, and that wasn't even the one I did because I ended up doing minus 5 pi and 4 here. Don't ask me why I did that, but so this one was in quadrant 2, quadrant 3, as we just drew it then. But so this one here, it's a different question I did in the notes. Minus 5 pi and 4. So we'll go 1 pi and 4, 2 pi's and 4's, 3 pi's and 4's, 4 pi's and 4's, 5 pi's and 4, and it's in quadrant 2. So sorry, I'll change it. So this might not say 5 pi and 6 in your notes when you get them. I'll make it 5 pi and 4 so that the answers work there. 9 pi on 2. So we can actually go around the unit circle more than once. So if you have a look here, I mean, if you write that as a mixed fraction, that would of course be the same as 2.5 pi's. So was it positive or negative? Positive. Okay. Right. So if we go in the positive direction, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, 9/4. It puts us on the boundary right here. So we say it's on the boundary between quadrants 1 and 2. Okay, so what I'm going to get you to do, just help you to consolidate it a bit, like because there's only going to be a couple of questions, just do a couple and check your answers. So if you have a look at questions 1 and 2 that are in exercise 9.4 on page 280 of your methods textbook, you could do a couple of those just to check your understanding before you go on. All right, so if you've done those questions, now remember that special angles that we've been talking about, and I can see that you've been using them, but we're going to extend that knowledge a little bit more. So remember that you derive those from those triangles, the one equilateral triangle and the one isosceles triangle, and you got these exact answers for the specific angles, pi on 6, pi on 4, pi on 3. So those are in degrees. Pi on 6 is 30 degrees, pi on 4 is 45 degrees, and pi on 3 is 60 degrees. So there are special angles. So for example, if we're finding the Cartesian coordinate of a trigonometric point, P equals pi on 4. So we've just said previously, we made the statement that, here we go, that sine of theta is y and cos of theta is x. So if we want to find the Cartesian coordinates of this trigonometric point, so it's pi on 4, so we go pi on 4 or 45 degrees to that there. We want to find the Cartesian coordinates here. So we know that x of the Cartesian coordinates is cos of theta. Our theta is pi on 4. So cos of pi on 4 from our exact values is the square root of 2 on 2. Similarly, for y, we need sine of theta, and we see that that's going to be square root of 2 on 2 for pi on 4. Oops, where have I? Another mistake there, sorry. Should mean pi on 4 in there. Right, so we find our Cartesian coordinates. So x is square root of 2 on 2, and so is y. And there it is there. And we by symmetry, you would expect them to be the same because they're the same distance up on the x-axis, on the y-axis. So by this argument, we can actually see where our calculators are getting the values for sine, cos, and tan for all our other angles. So say, for instance, we consider 20 degrees, and we want to find sine of 20 degrees, cos of 20 degrees, and tan of 20 degrees without a calculator. So it's actually kind of tricky, but we could draw a unit circle with a radius 1. We could sketch in an angle of 20 degrees, and then we could measure the values of x and y. So I've done a bit of a sketch here. I've just used a scale of 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, etc. on both axes. I've drawn in what I think is about 20 degrees. And then seeing here, I can see that my x coordinate here is 0.94 and my y coordinate is about 0.34. I used a calculator to actually get those exact answers. So once we've done that, then we can assume that if sine of 20 degrees is equal to the y coordinate, then sine of 20 degrees is 0.94. Cos of 20 degrees is going to be equal to 0.34. And tan of 20 degrees, remember our relationship, it's sine of 20 divided by cos of 20. So it's, in other words, it's 0.34 divided by 0.94. Roughly about a third, isn't it? What about those other angles that I gave you, which are those special angles that are right on the coordinate axis? So 0, pi on 2, pi, 3 pi on 2, and of course 2 pi on 2. Well, those are equal angles. They're equivalent. They're in the same place. It's just that they're one's 0, one's 2 pi. So let's consider what we'd actually get. So if so sine of theta, of course, is our y value. So have a look. What if we when we have 0 degrees? So 0 degrees is going to be right along the x-axis here. What is the y value there? The y value is, what did I do? No, y value is 0. That's right. So sine of 0 is 0. What about sine of pi on 2? Well, that's this angle here. And the y value there is 1. So sine of pi on 2 is 1. Cos of 0. Cos of 0 is the x coordinate here, so that's 1. Whereas the x coordinate for cos of pi on 2, that's going to be 0. So that's where those two values come. So similar arguments can be made for pi, 3 pi, and 2 pi. Of course, when we consider tan, this is interesting here because we get an actual undefined value. So we consider tan, remember that's y on x, or it's sine of theta divided by cos of theta. So when we consider the angle 0, the y value here is 0, but the x value is 1. So 0 divided by 1 gives us 0 for tan of 0. Whereas if we consider tan of pi on 2, y value is 1, but x value is 0. If we divide anything by 0, we get an undefined value, which is why you have in your table, you have these points where it's undefined. So what I want you to do is just pause for a second and try and see if you can get the same values that I did here for sine, cos, and tan of pi, 3 pi, and 2, and 2 pi, just using that argument and within the unit circle. So if you've done that, let's have a look at angles in other quadrants. So first of all, we've got our quadrants 1, 2, 3, and 4. In this quadrant, any value in here, of course, we've got the positive values of the x-axis and positive values of the y-axis. So x and y are positive in this quadrant, which corresponds to, because x is sine, positive value of sine, positive value of cos, and tan is sine divided by cos, so positive divided by positive, which is just going to be a positive number. In quadrant 2, we have y values are positive, but x values are negative. So it means that we have sine positive, cos negative, and positive divided by negative is going to give you a negative, so tan is negative. Similar arguments mean that we have sine negative, cos negative, tan positive, because negative divided by negative gives you a positive. Sine negative, cos positive, and tan negative. So a way to remember that without trying to work that out each time, we use an acronym CAST. It's a little bit annoying because we actually have to start CAST in quadrant 4. But basically what CAST tells you is which of the trigonometric ratios are positive in each quadrant. So in quadrant 4, only cos is positive. In quadrant 3, only tan is positive. Oops, my pencil's running out. And in quadrant 2, only sine is positive. However, they are all positive in quadrant 1, which is why we use the letter A for all. So cos, all, sine, tan, and it's just which ones are positive. otherwise they're negative. All right, so this is the tricky bit, and this is the bit that you need for your question that you were answering in specialist. So let's consider sine of 2 pi and 3, sine of pi on 3, and in fact I actually went a bit further than that. Sine of 4 pi on 3 and sine of 5 pi on 3. We want all of those. So what we're going to draw each of those angles. Sorry, it went further than I initially planned to. So I'm going to consider them. We're going to draw each of those angles on the unit circle first. So I've picked angles that are symmetric about the x and y axis. So I've got pi on 3, 2 pi on 3, 4 pi on 3, and under there 5 pi on 3. Now let's have a look at the x coordinates of the point P that's on that on the circumference of the circle there. So we know here x and y are positive. Over here we're going to get a negative x value and a positive y value. Here we're going to get a negative y value and a negative x value. Here a positive x and, oops, there's a mistake there, negative y. I should be negative in them. So what you should notice though is that, again, remembering that sine of theta is y and cos of theta is x, that the magnitude of each of the x values here, so each of these x values is the same. So the same distance along the x-axis in each direction. So the only thing that's changing is the sign. Here sine is positive, here sine is negative, here sine is positive, here sine is negative. Similarly for cos, because cos is the y values, the y value, the magnitude is the same of the y value in each case, but the sign's changing depending on cast. So let's consider y equals sine of pi on 3, which from our little table we know that that's the square root of 3 on 2. So so minus y would be negative the square root of 3 on 2. That's a bit hard to get. Go away, little thingy. So if we look at sine of 2 pi and 3. Sine of 2 pi and 3, we can see from our picture up here, sine of 2 pi and 3 has a negative x and a positive y. So in other words, but that y value here is exactly the same as the y value over there. So sine of 2 pi and 3 is going to be equal to the square root of 3 on 2, because sine of 2 pi and 3 is positive y is square root of 3 on 2. Whereas sine of 4 pi and 3, y is negative down here, and negative y was equal to negative the square root of 3 on 2. Whereas sine of 5 pi and 3, again, y is negative here, so it's also going to be negative the square root of 3 on 2. On the other hand, if we consider the cosine of these values, cos of pi on 3 is equal to a half from our exact value table. So then negative x is negative a half. In quadrant 2, where we've got 2 pi on 3, cos is negative because x is negative there, so it would be negative a half. Following that same argument, we see that cos of 4 pi and 3 is negative a half, and cos of 5 pi and 3 is a half. So can you see how cast is working in terms of that? So we see where we've got, I wish I could fit this on the one page, right? Okay, that sort of worked. So in quadrant 2, we expect that by CAS, we expect that only sine is positive there. And we do see that. There we go. Sine is positive, but cos is negative. In quadrant 3, CAST, both sine and cos should be negative. Yes, they are. And only cos should be positive in quadrant 4. And yes, cos is positive, sine is negative. So cast seems to be working. So what I've shown there is that by symmetry, we can use the values that we know in quadrant 1, so the exact angles, that's the pi on 6, pi on 4, and pi on 3. We can use those angles to find trig values in other quadrants. So let's have a look, and then hopefully you'll be able to answer your question. So to find the quadrant 1 angle required, we always consider the acute angle that's made with the x-axis. So if we do, say, as we did before, 2 pi on 3, then the angle that we want to consider that's is actually this angle that's made here. So if that was 2 pi on 3, then that would just be pi on 3, and that's the angle that we want to consider in quadrant 1. So hopefully an example will make it make more sense. So if we're finding the value of cos of minus 5 pi on 6, so what I would always do is do a quick sketch. It can be even quicker than the one that I've just sketched there, just so that you visually see where that angle is in the unit circle. So minus 5 pi on 6, we go in a clockwise direction from the x-axis. There it is. The next thing is to find the acute angle made with the x-axis. So if that's 5 pi on 6, and this is a whole pi here, then it makes sense that that bit there has to be just 1 pi on 6. So that's the angle that we're going to use in the first quadrant. Next, we need to use cast to decide if our answer is going to be positive or negative. So remember, we're finding cos. So in quadrant 3 here, only tan is positive, which means that the cosine must be negative there. So cosine is negative. Step 4, we use our quadrant 1 value and knowledge of our special angles to determine the answer. So we're finding cos of minus 5 pi on 6. And we know what cos of pi on 6 is, because remember that's the angle that we determined, the acute angle that we determined. And we know it's going to be negative of cos of pi on 6. So cos of pi on 6 from our little table, we know that that's square root of 3 on 2. So that's where that, and the negative comes in there as well. So let's try sine of negative 5 pi on 6. Sine is negative in quadrant 3, just the same as cos, because only tan is positive there. So sine is negative in quadrant 3. It's going to be the same acute angle because we're using the same minus 5 pi on 6. So it's going to be equal to negative sine of pi on 6, which equals negative half. So your question 7b that you had, I think you did the first part right. You expanded this the acronym CIS so that you had 3 equals cos minus 5 pi on 6 plus I sine of minus 5 pi on 6. But now we've just shown that cos of minus 5 pi on 6 is equal to negative the square root of 3 on 2, and sine of minus 5 pi on 6 is equal to negative a half. So I think you just sort of multiplied everything by 5. But in fact, hopefully that you see that that wasn't what you had to do. You had to find the equivalent angle, which was pi on 6, and then determine whether that was going to be negative or positive. And so if we multiply everything by 3 here, the answer drops out. So you can try questions 3, 4, 10, 11, and 12 if you want to just consolidate your understanding of that. So it's from exercise 9.5 on page 491 of your methods textbook. So some of them are in degrees, some of them are in radian, but it'll work out, you should be able to do both there. If you're having trouble with my explanations, there are a couple in the textbook. I'm just trying to work out which one it would be good to look at. There, worked example 12. So that's page 485. So that's another way that's probably similar to mine, but always good to look at 2 different examples. So do that one as well and then have a go at those questions. Good luck.